Hello, welcome to VHDL lectures. My name is Najim Lawal, and now we shall continue our discussions on VHDL intermediates. Here is the outline for this discussion. Essentially, we shall be discussing around decision making in VHDL, both within sequential statement and parallel statement, what kind of constructs like if statement and case statement that can be used, and for example, within the parallel statement, we can have with and when select statements. Decisions are the basic way of perhaps deciding the next path of execution. In hardware, perhaps decision making using if statement are not the most optimal kind of execution that you can benefit from hardware, but essentially we have to make decisions during our computation. So sometimes when we really need complicated and very not time demanding path deciding within the parts, we can perhaps use microcontrollers because they can be more efficient and lower energy consuming when it comes to simple branches between if statements. However, because most of these if statements are intertwined with heavy computation, then we need to have a controller or a central module for deciding, or a state machine for choosing between executions. So making decision in VHDL can be done within processes or in sequential statement, or at the architecture level within parallel statements. Here is a construct where we can have more information about sequential statements which are available in processes. The order in which the lines of code exist really plays an important role, and that means that if a particular if statement or sequential statement comes before another one, then the first one will be executed before the next step is executed. Although this does not mean that the value will be updated, because in hardware, especially in VHDL, the values are scheduled to be executed or to be updated at the next call of the process. So sequential statement essentially does not mean sequential circuits, which can be combinatorial, especially when we are using variables rather than signals, but it only means that the order of execution is stepwise and progressive. So when we want to implement sequential statement within processes and we like to make decisions, then we have the possibility to use if statements and case statements. If statement, we execute the first statement that follows the true condition. So we test a condition. If it is valid and if it goes to the Boolean level true, then we execute the statement after it. For analysis and debugging, it might be very nice to have a label, and here is a simple syntax about what if statements looks like. We have a label, we have the condition which is necessary with the if statement. So if condition 1 is true, execute statement 1. Else, if another condition is true, execute statement 2. So when the first statement is evaluated and is false, and another statement, condition 2, is evaluated and is false, we don't execute statement 1 and we don't execute statement 2. Then we go ahead and execute the statement following the else. The else is naturally not mandatory, but then it is highly recommended because it can help us to avoid latches in our implementations. So here is a Boolean expression of what happens when we implement an if statement. How can a simple or a complicated if statement be boiled down and analyzed into a very simple Boolean algebra? If, for example, we have a process that is sensitive to signals S, Y, Z, and signals A, B, C, and D. If you like to generate an output F for this set of input signals, then we can have, for example, a block of if statement look like this. If X equals 1, assign signal A to the output F. Else, if X equals 0 and Y is 1, then assign signal B to the output F. Else, if X is 0 and Y is 0, but Z is 1, assign signal C to output F. Else, if X and Y and Z are all 0, or they are not 1, depending on if signals X, Y, and Z are of type bit or type standard logic. If they are not all 1, then we can conveniently assign signal D to output F. So when we analyze this in Boolean algebra, we have a statement to the right that says that F essentially can be evaluated as X dot A plus X bar dot Y dot B plus X bar Y bar Z dot C, or X bar Y bar Z bar dot B dot D. So here is a translation, or here is the similarity between elementary Boolean algebra and if statement execution in hardware. Logic expressions with if, then, and else statements. So if, for example, we have a statement or we need to execute something, we can actually see, perhaps within the schematic diagram, if the synthesis tool supports this, we can actually see how this if statement has been executed or will be executed, so, or implemented in hardware. So essentially, if we have a process like this called SBus that has 3 inputs, we have XBus 0, 1, and 2, and we assign a signal do it now, a value 1 or 0 if all the inputs are not 1. Then we can actually have an implementation that is simply an AND gate. We don't necessarily have to use a multiplexer or complicated logic. This is sufficient enough to generate to implement this if statement with an AND gate, because the analysis of the statement shows that the do it now only get a signal 1 when all the inputs are 1, which is essentially what an AND gate is. Here is an example of an incorrect or unrecommended usage of if-then statement, because in this execution we have omitted the else clause. So here we have the same implementation as in the previous slide, but now we have forgotten to include the else clause, and what this means is that we have a latch. The system knows how to assign 1 to the output, but never knows how to assign the values 0. So what will the system implement if any of the incoming bits are not 1? Nothing will happen except that it will permanently always drive to 1. Case statements are alternative to if statements, and perhaps some people prefer it because they learn very easily to state machines, and of course they have a very structured way of knowing what next to do, and they can even embed other case statements and other if statements. So here we execute only one, the first one that evaluates to true. Like in if statement, these are sequential execution. So the first when clause or when condition that executes to 1 that has the true value, the statement following it will be executed. So here's the syntax. We have a label, which is optional, but it's good for debugging. Then the case keyword, we have an expression that can be evaluated into multiple choices, so not necessarily single binary or Boolean evaluation or true values. So we have case statement, we have selection expressions that can give multiple choices. So if we have choice 1 being the value of the selection expression, then the statement following choice 1 will be executed. And then we can always implement our choices or our selection expression to give different results that we have knowledge of. And the when clause, when other clause is very, very recommended, and it's the statement following it will be executed when none of the choices are satisfied based on the evaluation of the selector expression. So it's always very recommended to always have the when others clause. Here is an example of how to use case statement. We have case selection. It's a signal that can evaluate to value 1 or value 0, in which case we assume that selection is of type bit. If, however, selection is not of type bit, then we might have a latch in the system because we do not have when others alternative. So this implementation is very, very okay if we are very certain that selection is of data type bit. So case select is when the choice is 0, assign signal A to the output Z. When the choice is 1, assign signal B to the output Z. Equivalent implementation in hardware might look in if statement might look like this. Process select sensitive to signal A and B. We assign, if selection has the value 1, assign signal A to output. Otherwise, if it is B, if selection has a value 0, assign signal B to the output Z. So this assumes that the data type for selection is binary. Making decisions at architecture level or in parallel statement are similar to making similar statements in processes and in sequential approach, except that the order in which the statements appear do not really have any meaning, because we should be able to statically determine before we jump into this parallel statement what value should be executed. And to do this, we have constructs like with select when and then when else. So we should be able to know at the time we execute this parallel statement for decision making, what are the possible values that will be executed. So with select when statement is also known that as a selected signal assignment. It's a parallel statement. It's more or less like having its own sensitivity list, and it's based on the signals it's going to evaluate, and then it knows directly how to map an output value to how to map a value to an output signal based on the evaluation of an expression given to it. So select one of several values to drive a particular signal. This is based on possible values that an expression can lead into. So here is a syntax that says that we can use with a given expression, select a given value to the output if the value 1 satisfy the expression. Here is an example or relationship between how parallel statements can be implemented as sequential statements using processes. So here we have a parallel with select when statement that chooses an output given the value relationship between the choices and the expression that is evaluated. If you are to do this with a sequential statement, then we probably have a very large sensitivity list to our expressions based on the number of values and based on the number of choices in order to not generate latches. So here is the diagram. The output will be given a value from values 1 to 9 if choices 1 to 9 execute to 1. So here we can actually just flip through the process and say that if expression has the value of 1, val 1, then output signal will be assigned the value 1. And we continue this until we have an else statement that the expression should be given any given value or perhaps a default value 9. So expression in itself can be a signal coming or a port or a logical or arithmetic operation that can lead to many alternatives. Examples of how to use a with select when. So if you want to implement a 2-to-1 multiplexer, you can have, for example, with add, subtract, add subs, select. Opcode will be assigned the value add when add sub has the value of 0. Otherwise, opcode will be assigned the value sub when opcode has the value 1. And here is a schematic of how it can be implemented. We also have another example here that says that with A and B, select. So here we have a logical or a logical expression based on the fact that signal A is 2-bit and signal B is also 2-bit. So when we combine these two signals together in a logical expression, what are the values should be assigned to the output out? Well, we can do this by saying that when A and B evaluate to 0, 0, output 1, 0, 1, 1 should be assigned to the out signal. And this can continue all the way down to others. Others is default. It's like it's always necessary and recommended that we should always have an others in the implementation. We also have a construct here that says that we can have evaluation in the logical expressions, evaluations to the output. For example, we have X or Y. And if we look at the third example, with my integer select a particular value to the out vector. So if the integer has value 35, then we select 1F to the output. Otherwise, we continue. And then here is a range that says that when my integer has the value from 2 to 5, then we should assign the characters 2F in hexadecimal to the out vector. Otherwise, we assign characters FF in hexadecimal to the out vector. So this also means that we can use range in with select when parallel statement execution. The other alternative in parallel statement execution is called when select, which is also called conditional signal assignment. Parallel statements are sensitive to the signals that are listed in the choices and also in the conditions. So here we have a possibility to assign signal of value 1 to the out signal if or when condition 1 is satisfied. So at the beginning, condition 1, condition 2, condition up to 9 will be executed, and whichever one evaluates to true will be used to determine the output or the signal that will be assigned to the out signal. Implementation using sequential statement is shown to the right in the yellow block, in which we can have conditions, as many conditions as we like in the processes, and this condition can be signals or is block of signal, a group of signal that can be evaluated to a given condition. And then we have the values that will be assigned or that we need to read when we want to make the assignment. So if condition 1 evaluates to 1, then value 1 will be assigned to the out signal, and we continue all this until we get to the else clause. Here we have examples of how to use when else statements. These are also similar to the previous examples that we have seen. Opcode will be given the value add when add sub has the value 0. Else opcode will be given the value sub when add sub has the value 1. Else no operation or something like that will be assigned to opcode. So it's always nice to have a else and what to do when none of the conditions are satisfied. So here we have another example. Opcode will be given the value 1011 when A equals to 0, else 11 don't care when B equals to 0. Out will be given the value X or Y when A and B are both equal to value 1. In the third example, we also have it's a way of implementing priority encoding, in which case we can assign signal 11 to the out code, to signal out code when input 3 has the value 1 or input 2 has the value 1 and so on. So this will be executed depending all the values, all the signals in 1, in 2, in 3, in 0, they will be available at the same time because this is parallel statement. We have access to all of these signals, and what we are going to do now is that the first statement that evaluates to true, when in 3 evaluates to true, that's what we are going to assign. So here is a very simple test that says that what happens when all these examples are valid if in 1, 2, 3 and in 0 are all having the same value. So here we have the end of this discussion on intermediate knowledge or intermediate concepts within VHDL, and here we have been discussing decisions, how to make decisions using if statement and case statement within processes, and how to make decisions within parallel statements in architectural level using when and when statements, with statement and when statement. Thank you for joining us.